Hello everyone, and welcome back to the next new episode of TOXstream, the live show brought to you by Tox Academy. My name is Matteo, and I am your host as always, and I'm very happy to be here because this is our fourth episode already, so very happy that we managed to pull it so far, which is great. If you are new to the show, if you never saw it before, what we do here is to discuss of science and mostly on new alternative method to animal testing. And this is also the focus of AlterTox itself. If you don't know us, we really focus on promoting alternative method animal testing or new approach methodologies. And if you are interested in the same thing as us, I really encourage you to have a look at our website. We have really many activities in that sense, and I'm sure you can find something of your like. We are also everywhere on the social media, so you can also follow us there. And I'm sure that you can find something cool. You can also reach us. There is all the contacts there, and you can let us know if there is something that you want to talk about with us. We are always interested in meeting new people, focus on the same thing as us. While if you have been with us already from the beginning or from a few episodes, you know that we have always an expert that comes with us discussing the topic of the evening. And you can, of course, ask all of your questions, whatever you are, from Facebook, LinkedIn, YouTube, Twitch, doesn't really matter. Just write your comment on the chat, your question, and I will do my best to bring it to the guest, or maybe try to reply myself if I feel like it, or if I can. So you can use the chat. And at the same time, I'm just going to remove this. And today we prepared quite a very interesting episode for you. You probably saw already that we have a new intro, which is something that we didn't have it so far, so I hope you liked it. And we also have another news that is going to be a bit later down the video, so I'm not going to tell it now, but if you stick with us till the end, you will see that there is something new to TOXstream, and it's going to be interesting, so just stay with us till the end to find out what it is. While to jump on the story that we have tonight for you, we decided to focus today on one of the main, let's say, new approach methodologies when it comes to toxicology, which are in vitro bioassays. And they are one of the big ones because, from the name itself, you can see it's in vitro, meaning that it's really an opposition from using in vivo testing, which is one of the big part of toxicology themselves. And to put it very, very simply, it's basically the idea that you can take cells or part of cells from animals or humans and test substances on these cells. And then you can see what's happening, and you can take the results and try to understand how these substances would behave in a complete organism or even the environment, which is very cool. And you don't need to do use animal in that sense. And to understand a little bit how big of a difference using techniques like that might be in toxicology, I'm just gonna bring you with me in a very short journey on why and how we use animal in toxicology, and maybe why we should not do it in some cases. And this is starting quite a long time ago, actually, more than 500 years ago, with this guy, in a way, which was called Paracelsus, which is famous nowadays mostly for two things. The first one is his fashion style, because he always liked to have this hat with him. Every picture you can find online with him is always with his hat, which I found amazing. But the second thing is that he was kind of the first one to realize that when it comes to toxicology and toxicity in general, it's not a matter of how much a substance is toxic per se, but rather how much of this substance you are in contact with. Meaning that is the exposition and the dose. And in other words, it's basically the difference between watching just a few episodes of Breaking Bad at the evening, just, to relax, or being watching the entire 5 seasons in a single weekend, which, it might lead to some interesting life choice. Or, to use the words of Paracelsus himself, it's only the dose that makes the poison. And this is true, of course. And at the time, it kind of changed quite a bit on the way in which they were looking at toxicology. And actually, people say that he was the father of toxicology. And they realized that they had to find a way to test with these substances to understand if they were, dangerous or not for human. And they didn't want to do it on human, of course. So they decided to go for the very next best thing that they had at the time, which were, you guess it, animals. They didn't have many other tools at the time, of course. And this is something that worked quite well, honestly, for a long time. We are using it still today quite heavily. But even though they work quite a lot, because we are similar to animals, and animals are similar. Well, we are all animals, so we are all similar with each other to some extent. There is also, one major difference, and this is the fact that we are not a 70-kilo nightmarish rat. And they are not, tiny humans. There are, of course, differences between us. And in some cases, this can make a problem. It can create a problem when it comes to studies in toxicology. And some of them are scientific. For example, when we have to study substances in animals, one of the issues that we have to use a very high dose of this specific substance, because otherwise we don't see anything, which make a problem then to realize which one is the safety limit for humans, because the dose where there is an effect on animals is so high that you would never be able to actually expose yourself to such a concentration in real life, unless, of course, your name is Obelix and you ended up falling in magic potion all the time. But we know that's not good, because first of all, then you cannot drink magic potion for the rest of your life, which sucks. And also, this is not a real life scenario that apply to most of us, usually. And other issues are also the fact that when we use animals, we tend not to be able to test the heterogeneity that we have as humans, and the fact that we are all different within each other. There are differences in terms of ethnicity, in terms of subpopulation, genetic background, environment, lifestyle. And this is something that animals are not very good at, because they really are very similar with each other, and they tend to live together in a quite controlled lab environment. So the analysis that we have from them doesn't really apply in that sense. And also, we have more practical issue, because on one hand, it's quite difficult to really understand how many chemicals we are exposed to every single day. It's quite clear that we are producing more and more chemicals every year, and this trend is probably just going to increase in the future. And so we have to find a way to keep up. And animal testing, while might work in some cases, it's really very expensive, and it takes quite a long time to come to conclusion. And so this is probably not doable from a practical point of view. And then finally, of course, in the last few decades, probably we realized that, using animals to test substances for us, we feel a little bit like jerks sometimes. So it's always nice if we can find a way to avoid it. And so tonight, what we're going to do is to have a look at the in vitro bioassay, which are tools which are very, very useful in that sense. We're going to try to understand how do they work, what do they test, and in which way we can use them to try to solve a few of the questions that I listed, and maybe other questions that I didn't. And so after this very brief introduction, I think it's finally time for us to meet the expert that tonight is gonna explain us everything about the bioassay. So our expert tonight, I think, is one of the best that we could find for in vitro bioassay. I mean, she's a professor of environmental toxicology at the University of Tübingen. She worked a lot of doing her work on in vitro bioassay on water. She even wrote books about it. So I'm sure that she knows, and she's going to be able to explain us all the nuts and bolts of in vitro bioassay. And I'm very happy to bring on stage and introduce you, Professor Beate Escher. Whoop. Hello.
Hello.
Ciao, Beate. How are you?
Good evening.
Thank you very much for taking the time for being with us.
Pleasure.
Okay. So, to start, actually, before we go into the in vitro bioassay themselves, I would like to start to how you ended up stuck with the in vitro bioassay. I mean, how did you end up mixed with that? Why not, space travel or any other thing that you might have done in the past? Why you decided to go in this direction?
Actually, I started in that area without even knowing that I'm going down that pathway. When I started a PhD thesis where I had the task to differentiate 3 different modes of action on mitochondria, or on energy transduction, uncoupling, inhibition of electron transfer and ATP synthesis. And I actually developed an in vitro bioassay not really knowing that I was doing that. So I prepped my organisms. I got a method that was in fundamental biology, adopted it to applications, and basically I've been doing that ever since. I'm not going to tell you how long that is ago, but you can look at me and you see it's been a while. Yeah.
Cool. Oh well, then I guess you can also give us the perspective of how it changed during the years. But okay, then if we, before indeed starting and going through the how exactly do they work, I'd like to have your opinion on if you can say maybe for you the main reason why in vitro bioassays are absolutely important in toxicology nowadays. If you have, you have to choose just a few of the main examples.
For me, it's really a no-brainer because we really want to go away from animal testing and we want to test many more chemicals. I think animal testing is justified for certain mechanistic study, for understanding systems, but not for screening hundreds and thousands of chemicals, what we now have to do now that we put so many up and out in the environment. And so there's no way we can do that with any classical tests. So we had to come up with something different. And in vitro bioassays just have the kind of the right level, so they're fast. They give you lots of information, especially if you make the cell kind of that you can look into it and can tell what's happening, not just seeing if it's dead or alive. So I think that's just a fantastic tool. I must say I've also worked around the 2000s. I was really in love with in silico, so I was really thinking I can understand, if we just understand all the chemistry behind, then we can predict toxicology. But after a couple of studies, I realized it's actually the best point of departure for understanding mechanisms is to look on the cellular level and then take it from there. So I think this over the years, then that became a general opinion, and then a couple of years later, the TOXcast, TOX21 started, and I think now it's not debatable anymore. 20 years ago, it was debatable if you did in vitro bioassays, what would you learn from them? So it wasn't that clear, but I think that's not debated anymore today.
So you mean it's more a point of practicality because indeed you can do more things, but also a point of data production because you can also produce more data in that sense, if I understand it well.
Yeah, I think it's just a fine spot between having enough mechanistic information, enough realism that you can really do in vitro to in vivo extrapolation directly, and that you can still produce a lot of data that you wouldn't be able to produce with animal testing or with any more complex system. And then, of course, you can have in silico tools, you can produce many more data, but your predictability is not as good. I think if you see an effect happening in a cell is the smallest units. We're made up of cells. This is going to happen also in an organism. Might be a little bit higher, lower, a bit more sensitive, a bit different sensitivity in different organs, but in principle, there's a lot of commonality.
Mm-hmm. And so before we go indeed in the how easy it is maybe to translate this data on a more higher scale level, where do we use this test? So we can use them to anything. I mean, I know you worked a lot with water, but it is easy to use them also on other matrices, food or on biological materials, or there are differences which makes a difference or not?
Well, if you're interested in organic chemicals, I mean, of course, there's also metals, there's inorganics, there's pH, there's all sorts of stressors, there are indirect stressors when there's a dam build or so, which will harm, or when we have noise pollution or so. But if you just think of organic chemicals as stressors, and you can, is there a way to dose them in a way, according to Paracelsus, dose makes a poison, in a way that you know what the dose is and you can reproduce it. And so basically, you can test anything that has organic chemicals and you know how the dose, what you add, translates into the internal concentration. And then you don't always need to measure the internal concentration or so. You just have to be sure that the chemicals are taken up and will do their thing. And so once you have this relationship established, we have done that for many years and we fine-tune on that, then you can test single compounds, you can test mixtures, you can test anything you can extract from a complex sample. provided your extraction is good, that you're not, that you really can isolate the chemicals, that you can clean up, that you can keep the mixture in that composition. And that's the easiest, most likely, I would say, for water. Because for water, we have solid phase extraction. You co-extract a little bit of organic matter, but that doesn't disturb if you have cell-based assays. This would, for instance, disturb if you have free enzymes or receptor binding assays. So you're kind of good. We know, we have done a lot of research to find out that you can dose the chemicals in a defined way. Now you can move on to more complex matrices, anything, pencil, you can extract it, provided you can really get all the plasticizers and everything out. And there's also with ink. Ink might disturb the signal, so you have to also be aware of that. You know, like you might have something fluorescent that then disturbs your detection method. But provided you can have all of that under control, you can put anything in. I mean, we've been putting turtle blood, we're working with beluga, blubber, lots of marine mammals, like we've done dolphins, humpback whale, all sorts of whales. We've done people, I mean, not entire people, just little bits of them, blood. Can't do urine, that's a problem, because that would be very easily accessible, but then we have just the products that we, after detoxification. So we don't have the original ones, we really have to go into body fluids. But we've been trying earwax wax. It's a bit hard to get out. I think since I did a test on myself, I don't hear that well anymore, but it could also be old age. But you can get the persistent organic pollutants in your earwax too. Tissue samples from surgery. So you can take any tissue. So we have, it's more tricky when you have lipid-rich tissue. You have to do a few cleanup steps, you have to do certain methods, but provided the chemistry, kind of the sample preparation is fine. And for chemical analysis, you also need a good sample preparation. Otherwise, your instrument will blow up and will break down immediately. And so once you have a similar type of cleanup before, you can put anything. I mean, I've been putting pretty much anything you can name. I'm sure next time I meet you, you'll bring something up that I haven't put into a bioassay.
Now it's kind of a challenge. No, but that's very interesting. Of course, I mean, the technique is just as good as what comes before. But indeed, it's super interesting that you can do so many things. And in terms of which cells you use, are we using everything, or there are maybe some cells that we don't really? It's very hard to use them, or it's very difficult to then use them to translate it to human, or?
Oh, that's also a question we can talk for hours about it. So in a way, you can take it very simple. You know, you can say feasible, reproducible, so you can take bacteria and yeast, and then everybody can do it. You don't need a special lab. On the other side, you can take stem cells, and that you then specialize and all of that, and that only a super specialized lab can do. Our lab doesn't have the facility even. There's kind of a middle way out that a lot of labs are using, are immortalized or cancer, human cancer cells that are fitted with a reporter gene. So because otherwise you can just see cells dead alive, or you can also do staining, and that's also very trendy right now. So you stain the different parts of the cell with different dyes, and then you can basically visualize the morphology and also then the functionality by, for instance, staining mitochondria, or staining nuclei, staining different parts of the cell. But that's just coming, so that is a method that hasn't really been brought into environmental or human biomonitoring. But what's become very popular and what's very widely used in water quality monitoring in risk assessment of chemicals and mixtures are really these reporter gene assays, where you have a mode of action of interest, either molecular initiating event like a binding to a hormone receptor, or a key event, something like an adaptive stress response, and you just add a reporter gene to the cell, and that's also something that specialists would do. And so we are just using these cells, but it's also important that many people use similar cells. So there's this big initiative from in the US, US EPA and NIH, and they have this initiative TOX21 and TOXcast. And so they use certain cell lines, they screen thousands of chemicals with them. So why not using exactly the same cell lines? I mean, they're either commercially available or you can get them from a colleague. And so then everybody's using similar cell lines. And so you can build up a database that you can use to compare, to benchmark, to do mixture modeling from single chemicals to mixtures. So this is kind of what has developed over the time, that if there's a few popular assays, people always develop new ones. We also always try, and we're also constantly developing new ones or adopting one, them from pharmaceutical science, then for our applications. So that's a little bit how things happening in this space.
Okay, so there is also quite of a collaborative aspect to it, because of course, yeah, the more data you can produce, the better you can put them all.
And some assays, I've forgotten about this. Some assays are even validated by OECD guidelines or ISO guidelines, and so then it's pretty prescribed how you do it. And so then anybody, once you have the materials, you can do the assay.
And maybe in that sense, what it is that you measure usually? I mean, I guess you can measure whatever you want, but what is the most popular direction in which you go usually, or maybe the more established one?
That's really the application that you what people. So we work together with a lot of colleagues. So we are often supporting acts. So somebody has maybe a treatment system, drinking water, and they think about replacing chlorine with something else. And then you would need assays where you can detect disinfection byproducts, or you have a child cohort where you look at learning disabilities and other neurodevelopmental effects. And then for such an application, we would go with a neurotoxicity assay. That wouldn't cover all the aspects, but kind of be an indicator. And in water, what's very popular in surface water is hormone-like effects like estrogenicity, because when the wastewater is not treated well enough, we still put estrogens in the river, and that can do harm to fish health and reproduction, mainly reproduction. And so that's also something we don't want that. So we want to make sure that the estrogen levels are low enough. And so it really depends on, so we're always talking with people who are collaborating, what their interest is, what they want to investigate, and then you match a bioassay, and sometimes you can't match a bioassay, and then you have to find a new one.
Okay, but and then maybe that was the question that I have more difficulties to apply myself. How easy it is to go, once you have your data, then to translate it to, I'm assuming most of the time to human, but also to the environment. How easy is this connection? How many other data? Do you need other data to go in that direction, maybe from other techniques at the same time?
Yes, I mean, the easiest, of course, you do just a correlation. So this is, for instance, done for fish embryo assay, which is also considered an in vitro assay, or with fish cell lines, and then you make a correlation with fish acute toxicity. And if it's a line, then you can have kind of a simple predictive model. It's not all that easy when you really go from human cell lines and a certain reporter gene assay to what's happening in vivo. But there have been many tools developed over the last years that can do that. So essentially, conceptually, it's like you have, when you have the internal concentration in your cell, and the effect that you measure would happen at exactly the same concentration in a cell in your body. So now it sounds simple, you just need to translate what the dose in your cell means for the dose in your body. So what's the easiest for the body? So it's the blood which is circulating. So all the chemicals are taken up, they're circulating with the blood, they're taken to the liver where they're degraded. And so basically what you want to do is you want to find out about the blood concentration. And then you say, well, the cellular concentration in my assay equals the blood concentration in terms of the blood cells. And then you just have to go back, what are the freely dissolved concentrations in your blood, how does it distribute over the people? So you have physiologically based toxicokinetic models or pharmacokinetic models, and then you can calculate back to the dose that people have received. And that's how you make that link and how you can then make the risk assessment.
Okay, so there is a strong necessity to link different techniques in that sense.
Yeah.
And are there some techniques, because you said before, extraction needs to be, of course, well done. So there is the X aspect needs to be connected, and then PBK might be another aspect. Are there also other techniques that are very linkable, let's say, with in vitro bioassay in that part?
I think what's really important is when you think of applying it for mixtures, because that's really a strength. You extract everything organic out, you test the mixture, and then you want to compare it with the chemicals you can detect with chemical analysis. And so here we've done amazing steps over the last 20 years or so, going from, you could publish a paper when you analyze 10 chemicals in a river, to now people having thousands of known chemicals and or hundreds of known chemicals and thousands of non-target just features, where they know there's a chemical behind, they don't know what it is, but they know it's organic, they know it has a fluoride or something like that. And that gets really exciting when you then start connecting this on several levels. Of course, you can do the very simple, that's our daily business. You do mixture modeling, you know the chemicals, you know their potency, you calculate how much of the effect that you measure you can explain by the known chemicals. So that's kind of the standard. The next level would be that you look at signatures, so that you look at groups of chemicals, and you bring in suspect screening, you bring in non-target analysis and make those connections. And both methods, I think, are really powerful. I mean, it's nice to know you have certain chemicals, but often the ones that are there on high concentrations are like caffeine. They're not that harmful, a little bit, but not too bad. So you always find them at high concentration in your untreated wastewater, but also in your blood. And so you want to have the potency, you want to make that connection. What does that mean? And then, of course, you need to know what's okay, because now the test systems are so sensitive, so you will almost always measure something. I mean, we can even tickle effect out of drinking water. And so you have to say, this effect, I can measure it, but it's okay. It's the same like we had decades ago for pesticide concentrations in drinking water. So when it was detectable, it was bad. But detection limit was about 0.1 microgram per liter. And I hope that's right. Don't take me down on that. A certain value. That was basically the detection limit. And then detection limits got lower and lower. And then you would detect more and more chemicals. And then at this stage, you have to say, this concentration acceptable, it will not do any harm. And above that, it's a problem. And we have to do the same for bioassays. We have to say, this bioassay effect is acceptable. If you have that level of chemicals that cause that effect, you should be cautious. You should do something, like you should reduce your exposure. You should treat your water. You should excavate your soil and not grow crop on it, but just grow some other plants on it also, so that you can take action. Just because these tools have become very, very sensitive over the years.
Mm-hmm. And okay, here, because you listed a lot of techniques, a lot of different interaction here, so I really picture a very interdisciplinary approach here, and I wonder how easy it is to mix all these people together, because as you said, it's not trivial to have a lab that is able to do everything at the same time. So I'm assuming that a lot of this needs to be inter-laboratory efforts. How easy is to align everybody on one specific direction?
I mean, as you know, whenever you build a house, people have to communicate, and it's not always easy because people are people, but I think that's also the fun of it. And I always took a lot of pleasure, at least back in the days when I was still able to have enough leisure time that I could go out sampling, put my own passive samplers into the rivers somewhere back ways in Australia, or were working on the plants and putting samples in, working with engineers. I think I had a little bit of fable with for the wastewater and advanced water treatment engineers I worked a lot with. They're just very like genuine, cool people that just work hard, and it was always a good back and forth. So I think it just grows. It has to grow, and I think a lot is trust that you deliver. Like if you promise something, that you deliver results, and if there's problems, that you tell what problems there are, and that's how you build up collaboration. So I think research has become super collaborative over the last years. But in that area, I think we've been collaborating much, much earlier. I don't just know a single paper that's a single author paper. You know, I mean, now sometimes we have 40, when we have 20 labs involved in that jointly work on one type of water or on the same water samples. That's maybe a little bit over the top at times, but it needs sometimes these efforts where everybody puts in, where you find a common language. I think finding a common language has also been very, very important. And that's really how we started, why we started writing a book. I never wanted to write a book. I did my PhD with René Schwarzenbach, and I suffered through all 3 editions of Environmental Organic Chemistry, and I know it by heart. And so I said, I never ever write a book in my life. But then we did a lot of applied work on water recycling, and they always had many questions, and we could answer them, but basically every answer, you know me, I mean, that's just the way I am, is like citing 3 papers that I had just recently by chance written and then sending that to them. So some people might.
The best, why not? Of course.
And so then they said, why don't you write it up? You know, write it up in simple words. And then we also realized when we started working together, everybody, you know, has a different way of terminology, how you dose water in cells. You know, what's the equivalent? What is your dosage? How is your terminology? And I think writing that up and really thinking about how you express that also to people who are maybe not in your field, making it clear, make it concise, make it not just simple. I think it's not simple, but make it good, make it clear. I think it grew a lot, and I've really seen, so we've published our book, the first one 10 years ago, and the second edition was just out last year. And the field has really grown, and I see now it's also easier to read other papers because people use similar terminology. I mean, we've been meandering a little bit over time. It's not always consistent. We had just a couple of those discussions today. Why you use IC when you use EC, when it's inhibition, when it's effect. But you know, we started to think about that, and these are little details that just then become very powerful because they allow us to speak in a common language. And I think that is what has really happened. And that's why these tools have become so successful.
No, I definitely I agree. Every time I have to read a paper and there are more than 10 different acronyms, I don't, because I say, no, I'm not going to understand anything. And then when there are different papers citing the same thing with different names, it's always a nightmare. So it's great if there are efforts in that sense, indeed. But so what was a nice experience to write the book itself. So
it's never a good experience, especially the last one. I'm not going to comment on that. And Christmas and Easter. It's really nice to have an Easter. It's nice to have Christmas. So, but that's also our own time management. But it's always fun. I mean, I've been writing with my 2 colleagues from Australia. That actually came the idea when I was stuck with the first lockdown of COVID, and the 3 of us, we lived in different places in Australia, and we couldn't see each other. The border between New South Wales and Queensland was closed. So I came all the way from Germany. Then they they closed the borders, and then we thought, what are we going to do? And we said, we could write a second edition. It wasn't a good idea in hindsight, but that's what we did then. And I just had the chance to see both of them a couple of weeks ago, and borders have opened again. And to see both of them and celebrate a little bit our joint achievements. Because again, this is something you can only do together in a team.
Mm-hmm. Well, it seems a better way to spend the lockdown that many of us did, that was just on the couch doing nothing. So well done. And I think now we can actually I can actually bring you the news that I wanted to talk about, because we decided to add a little piece to TOXstream. And so for now, I will just say hello to Beate. We'll bring you back in a few minutes. So don't leave us. Just stay with us. And because we decided to add a little new segment, mostly because we spoke a lot about very general and abstract part of techniques usually, and we decided that it might be a good idea to have also something more concrete and a little bit funny. And so we came up with this idea of these more concrete aspect of our topic, and I'm not going to be the one doing it again. So you are going to see a new face from EcoTox that I'm very happy to introduce. She is a very scientist on ecotoxicology, so she knows her stuff, not like me, and I'm very happy to bring on stage and introduce you, Leonie. Ciao, Leonie. Ça va?
Hi,
You good?
Matteo. Hi, thanks for having me.
Okay, great. So I know you know absolutely everything, so I am going to leave. I'm going to leave you the stage, and please enjoy.
Thanks. Yes, as Matteo said, I have a background in environmental science, and I today want to talk to you a bit more about the reasons why we do environmental monitoring, why we do chemical safety assessment of chemicals to make sure they can't actually do harmful effects in the environment or cause toxicity in us humans. So today I want to look back in history and talk about worst case scenarios if actually no safety assessment or no sufficient safety assessment of chemicals has been done before chemicals are introduced in the environment. And I want to talk today about the case of DDT and birds of prey, and specifically bald eagles. So we have to look back quite a bit in history. So this is something that took place in the 1950s, 1960s. And this case mainly took place in the US. And scientists there noticed that the populations of many bird species declined rapidly, specifically of birds of prey. So birds that feed off of other animals. And scientists tried to find out then what caused this decline of the populations. And they looked at different aspects, and they found that certainly changes in the habitat of these animals certainly had a role, but it couldn't explain fully the effects they saw on the population. So they did a little bit more digging, and they actually found that a commonly used insecticide, namely DDT, and its metabolite, DDE, could be found in these animals. So they thought this might be a clue. Probably this insecticide is causing these large-scale effects on the populations. So they tested DDT in toxicity tests with the adult birds and found nothing. The birds didn't die. So they thought a bit more and looked at more mechanistic ways in which chemicals can cause effects on animals. And they found that the chemical DDT and the metabolite DDE actually had effects on the reproduction of birds of prey. They looked at the eggs, and what they found was that DDE actually caused the metabolism of the adults to change, which led to lower numbers of calcium being incorporated into the eggshells, so the eggs were very thin. And when the adult birds tried to sit on the eggs to incubate them, the eggs broke and the embryos died. And this is how they found and could prove that DDE and DDT was actually responsible for the effects on the population of these birds. And for me, this shows two things. One, that the chemicals that are introduced by humans into the environment are actually can be responsible for severe effects on animals that can actually happen on the population scale. And this is something that was fairly new in the time where this was discovered. Many people thought that the environment is so large and ecosystems are so strong to distortion from the outside, and us producing our chemicals cannot have an influence in that. And these were the first times where it could be shown that we are actually able to influence animals in the environment with the chemicals that we use. And the second thing that this tells me is that it is important to not only look at mortality in adult animals as an endpoint to find the active substances and the mechanisms that can cause these effects on environmental scale. Now, I want to do a little quiz with you. I will present you 4 cases that are similar to the one I just explained, and I want to invite you to put your answers then on Slido. Here's the code that you can use on slido.com to see the quiz. The 4 cases I want to show you are all cases where chemicals potentially caused effects on environmental scale, and you can then put your answers on Slido if you think these are actually true, because I might have slipped one that I made up into the choices. You can also put your answer that all of them are true, or they are too outlandish and none of this actually happened. So the first example I want to talk about are the effects of PCB. These are chemicals that are used in industrial applications, had on otter populations in Sweden in the 1950s, where when these chemicals were still largely introduced into the environment. And they also had effects on the reproduction of otters, and the litters of the otters were small or died, and this caused a near extinction of these animals in Sweden and large declines of otter populations all over Europe. The second example is a bit more recent. So this happened a couple of years ago, where vulture populations, so also again large birds, their populations declined of up to 97% in the countries of India, Pakistan, and Nepal. And the underlying cause was that diclofenac, so a pain medication, was used in these regions for livestock. And diclofenac, maybe some of you know, I also recently had to use it as the active substance of Voltaren, so a pain gel medication that you could put on your skin and that eases pain. And diclofenac was used in livestock in these regions, and when the animals died and they were out in the open, vultures came and fed off of them. This way they incorporated the diclofenac, and apparently diclofenac in these birds leads to kidney failure, and the population nearly died out. The third example is that of gastropods, so snails and mussels in the Atlantic Ocean, where we had also near extinction of some of the species due to the usage of special paints on boats, so-called antifouling paint, so paint that prevents the degradation of the outer shell of the ocean, of the boats. And these active substances in the antifouling paint led to gastropods undergoing sexual transition, so female gastropods developed male sex organs, which led to, of course, effects on reproduction, and then also, again, near extinction of certain species. Fourth example is a population decline of the European eel. What caused the population decline for the eel in European rivers was the use of certain pesticides and use too close to the river. So there were large portions of spray drift, which introduced the pesticide into the water. And these pesticides had neurotoxic effects on the eels, which then again led to population declines of these species in the rivers. So I invite you to put down your answers in slido.com, and I'm happy to see what you think, which of these examples can be real, which of them actually happened, or if you think this is too weird, this didn't actually happen. And then I also want to invite Beate again back to the stage to look at me, to look together with me at the results that our viewers put in, and maybe discuss what you think about these historic examples that I presented here today. So if you look at the examples that happened in the past, because you work a lot with environmental samples and chemicals in the environment, how do you feel when you look back in time at these examples and the scale of effects that chemicals can have on animals?
Well, in hindsight, many we thought we could basically explain, but when you then have the most recent case with the water population decline, it was really a criminal story and a big enigma, and it took a lot of evidence until they found it out. So, which means that only happened a couple of years ago. I can't even recall exactly how long ago. I've been out for a moment. So I think it's really difficult to say that. These are spectacular cases, right? And it's good that we're talking about those spectacular cases, because they also with these animals that are so cute, like the otters, or like the vulture population that has then a lot onwards effect with the decaying cows that are then not eaten by vulture anymore and all of that. So these spectacular cases need our attention. But chemicals are actually silent killers. They are kind of, everywhere, and we don't notice until it's too late. And I think that's probably something what we always have to keep in mind, that it's not just those few spectacular cases that get a lot of attention, but chemicals are everywhere, and many turned out to be problematic by some mode of action that we hadn't really anticipated before. I mean, like now in hindsight, diclofenac, it's a kidney damaging agent. Yes, we should have known, but nobody thought of it. Nobody thought of those consequences. And for me, that's also very similar to all of those foreign species they introduced to Australia that. Then suddenly there were rabbits everywhere, and no more birds, and because they just had thought about one way and not really thought about the complexity of the system, and probably it's not possible to always anticipate all adverse events, and that's why you should act precautionary, especially when it's in context of chemicals.
Exactly. And how, in this context, will in vitro bioassays help us to evaluate the effects of chemicals and to make sure that these, as you say, spectacular cases, but also not so obvious effects on environmental structures do not happen again in the future?
Well, that's a tough one. I mean, you really have to hit the right mode of action in a way. So I'm not sure if in vitro bioassays would be really good for exploratory work to identify totally new endpoints that we hadn't looked into before. It's more if we're aware of a problem, we can see the extent of its magnitude. Like I said before with neurotoxicants, if we have an assay that can quantify it, we'll be surprised how many chemicals act via that mode of action, how they act together. I think that's really the topic. I mean, that tributyltin does a lot of ugly stuff, and that in whichever assay you throw it, you'll have a red alert, but that it really leads to the female snails developed male sex organs, which is actually a myth too, right? Wasn't that just recently revealed that that's not really correct? But that you have kind of from an evident effect of a chemical that is an evident effect that you get something that is happening in a totally different place. That's really hard to predict. then you can only predict when you have a pathway that you can predict, when they have many examples. So the free cases, I think it will always be hard to predict them. You often stumble over them.
Yeah, but what I found interesting, like looking back at the example of DDT in the bald eagle, is that, I mean, this is very crude translation of in vitro bioassays and mechanistic toxicity to what they did back then. But what I found interesting is that first they tried to just look at mortality and just fed adult birds the DDT and also looked at the metabolites, and they didn't see any effects. But then if you look at more mechanistic specific endpoints, in this case just reproduction, which was maybe back then a bit more mechanism specific, they were able to show that there's a relation between these chemicals and the effects that they saw on the population level. But of course, you're true. It's always hard to predict out of all of the things that chemicals can do.
Although, where is it? Have you all read Rachel Carson's Silent Spring? I mean, when it comes to DDT, she actually predicted everything quite well, but nobody listened to her. So I think we always know much more, and she's a good example. In 1962, she understood the whole problem, and there's nothing wrong. There's nothing exaggerated, a little bit that fable at the beginning, but she understood what was happening, but nobody listened to her.
Yeah.
You know, I think so. It's often we know, but we don't act.
Very true. And it's good that you bring her up because, that's the where I have this example from, and it's a very important book. And she did very good work back then and brought attention to this issue. And her work and making it public contributed to the knowledge about these cases, and then in the end to the banning of DDT. So if we look at the results, so people thought that female snails developing male sex organs because of boat paint doesn't sound like something that actually happened. And I agree, it sounds very outlandish, but it did actually happen. But I think it's interesting, Beate, you said that the actual morphological changes, the evidence isn't as strong anymore, it doesn't hold up. I haven't heard about that.
I think I had listened to a podcast. See, this is happening when you listen to a podcast and do something else at the same time. Somehow it rings a bell, but don't put me down on that. I have to find it.
Well, I will read up on that. But to my knowledge, this is an effect that did happen, and there is a scientific term for it called imposex. And it was found to, at least TBT was found to be the causing agent of the decline in populations of snails in the Atlantic Ocean. So this is actually true. They are not all true, and 20% of our viewers found the correct answer. I made up the story about the European eel going extinct because of pesticides. So this is something I came up with. But as Beate said, the example about the vultures is true. This happened rather recently, and it is a pretty mind-boggling case when I heard about it, that this actually happened, and then also the results of it. So it's not just the effects on the vulture populations, but then also in response to that, that the livestock that is left out to be open, and until then, vultures in these parts of the world were the natural garbage personnel, which were then not able to clean off the carcasses of the livestock, which would then just lay out to rot. And this had many effects, then again, also health effects for humans. And interesting case to read. So,
but can I just make a remark? I also put European eel in the answer, but I had some doubts because can you remember Schweizerhalle? I mean, you were born then.
Yes.
But that really extinguished, at least in the upper part of the Rhine River, extinguished the every bottom dwelling fish species and especially eel were very badly affected.
Yes.
So they were wiped out for a long time, but it wasn't a pesticide. So I think, what was it back then in Schweizer Halle? It was a dye, I can't even remember.
I thought it was pesticides actually, but I'm not sure.
Okay.
So for the people who don't know this event of Schweizer Halle, but yeah, Beate, you're right. This is actually what inspired me to come up with this example. There was in 1980.
Sneaky you are, huh?
Yeah. In 1986, there was a huge fire in Schweizer Halle in Basel, I think, and the fire department came to extinguish it, and back then there were no holding tanks to hold back the water that was used. So the water, along with all of the chemicals that were produced at the site, came into the river Rhine. But yeah, you're right, there might have been a dye also involved in this, because the river turned red for this time, which alarmed a lot of people. And it did also have effects on a lot of invertebrates and also fish. And there are pictures of eels, just riverbanks covered with dead eels, because they are very sensitive to the chemicals that were introduced to the Rhine. But the Rhine since then recovered from these effects, and it also led to the introduction of some monitoring stations that constantly monitor the quality of the water of the Rhine.
And I just looked it up, so we're all right. So stored chemicals included urea, fluorescent dyes, hence the color, organophosphate insecticides, mercury, and organochlorides.
We're both correct.
Yeah, quite a bit mix of nasty stuff.
Yeah. Yeah, it was two things, 1986. It was Chernobyl and then Schweizer Halle, two huge environmental catastrophes that happened back then. And I was born, which...
See, I thought. It was actually very formative for me too, because I was studying chemistry, like pure chemistry. I was a synthetic chemist, and in 86 I went to the US for my junior year. Now you can calculate how old I am. And I came from Europe, and I just lived through all of those things. And so I took environmental ethics and environmental science. I gave a lot of talks. I remember I gave one talk about the Green Party that has just been emerging. We believed back then as the first in Germany, which was true, that there's an older Green Party in Tasmania. But that was for me also very formative years. And since I also studied that in Switzerland, then later, I really really changed my perspective, got more and more interested in these environmental issues, and thought might as well make a profession out of it and not just a hobby. Yeah, it was very... And then we taught, I can't remember the chemicals anymore, because for years we had all the Schweizer Halle example in our chemistry lectures, and how long does it take to degrade?
Yeah, it is a long time ago.
Mm.
So thank you very much for this chat about the more environmental aspects of in vitro bioassays and all of the effects that have happened in the past. Then I want to hand over to Matteo again. Thank you again to Beate and to Matteo for having me here today. It was a lot of fun.
Thank you, Leonie.
Thanks, Leonie.
Well, don't worry. She will be back with more very scary stories in the future in other episodes. So thank you very much for that. I hope you enjoyed it.
Can I just say one more thing?
Of course.
You still find DDT in our blood, and we detect it with bioassays there.
Wonderful.
No, it's not wonderful. It's pretty sad. And it's also DDE and other metabolites, but it's still there, unfortunately.
I was already scared by the fact that there was this news of microplastic in the blood. I guess there is more, yes. But not know sometimes. Okay, so to close, actually, I'd like to ask you one last thing on the bioassay, but rather more on the regulatory toxicology side. To have your idea and your knowledge on where these bioassay that we know that can be used everywhere, where are they actually used right now already? in which aspect they can be used or why they cannot be used, and like that.
There's multiple ways. I'm not happy with it. There could be more, but in principle, alternative test methods are part of REACH. So they you have an integrated testing strategy, and in vitro bioassays could be part of it. Unfortunately, it's not as heavily used as it could be, and so there's really room for improvement. I think when REACH was started and the company started to work on it, they were not ready for the bioassays. In contrast, in the US, they were lagging a little bit behind. They weren't as modern as REACH, but they made a commitment by 2035. They're not going to do any more animal testing for risk assessment. And so then they also, set up the whole TOX21 strategy. So they got the data, they got the tools, those high throughput tools, all the computational tools, the whole CompTox program. And so they're committed to be there by 2035. And there's already companies that are fully committed. I shouldn't make any advertisement, shouldn't name a word, but some of the consumer some of the consumer product companies, the guys who sell shampoo and all of that, I mean, they still have to test their chemicals, or they have cosmetics, then you're not even allowed to test with animals anymore, which is good. Of course, I fully support that. But they are really forced into that in vitro space, and they're doing magic stuff. So it's pretty impressive. But legally, all that work we're doing with water quality monitoring and all of that, there's only one place in the world where when you recycle water, you have to do bioassays. Do you know what place that is? I think I told you already.
Might be, and I forgot. Sorry.
It's California, state of California.
Okay.
So they're very progressive. So they have, if you recycle water for indirect potable reuse, you have to run an estrogenicity assay and a real hydrocarbon assay.
Okay, and since when?
Couple of years, I think 2 years or so. I'm not sure how they're faring, but it's been long in the going. So I think they started thinking about that. I remember we were traveling. We had a couple of really nice invitations to California to show how bioassays work, help with setting them up in the lab in 2011, 10, 11, 12 maybe. But there's very strong research going on there, very strong political wind, progressive, and they made it. I would not have given it that it's California. I would have just thought it was almost Australia, but then they didn't do it. I mean, anybody who is recycling water for direct or indirect potable use should have bioassays, in my opinion, and not just random 20 chemicals as markers, but should be playing safe.
And that you think is more of a legislative issue, scientific issue, communication?
No, I think science is there. Science is getting better every day. Mm-hmm. It's now really to implement that into regulation, but it gives me a lot of hope that for certain applications, you don't need for all applications, but for certain things that you use these tools not just to do research, not just to write papers, not just to increase your knowledge, but you really use them for what they're useful for. That you use them as a monitoring tool in water safety planning also. And a lot of the practical part of my work is, I love the science, and I love playing on working on the details and answering the detailed questions. But I also spend a lot of time trying to push it on the political agenda, Water Framework Directive, etc.
Yes, definitely a useful and necessary work as well. Well, I think that's all the time that we had for tonight, unless there is something else that you absolutely want to share with us, Beate. No, I think we took enough time from you. Thank you very much for this time. I mean, at least for me, it's more clear than before what we can do and we cannot do with bioassay. And hopefully they will be used more and more in the future. Again, thank you very much for watching us. We are going to be back in 2 weeks, the 27th. We're back again with another episode, so don't miss it. You can follow us on social media. And next week, we're going to publish the guests that we're going to have. And until then, thank you very much for being with us, and good night.
Thank you very much. Bye-bye, Matteo.
Bye-bye.